This video is the last and final part of a 4-part series titled How to Repair Anything Without a Manual. Now, like I always mention in previous videos, if you haven't watched part 1, part 2 and part 3, I do recommend you go back and watch those first, as it will make everything easier for you to understand. And you can find the links for those videos in the description of this video below. Now, first of all, if you've made it this far, I'd like to congratulate you and thank you for having the patience to bear with me. We have covered a lot of stuff and we've got a lot more stuff to cover in this video. So grab yourself some popcorn or make yourself a nice cup of tea and let's get started. Okay, so in the previous video we did a multimeter test in diode mode and we came to the conclusion that this chip here is possibly faulty. We located that chip online and we've ordered them in. Those chips have arrived, and what we're going to do now is, in this video, we're going to replace this chip. Now, to replace this chip, we're going to use 3 tools. We're going to use the microscope, we're going to use the soldering iron, and we're going to use the heat gun. So the first tool that I'm going to introduce you today is the microscope, and then what we're going to do is we're going to have a look at the replacement chips that I ordered under the microscope. Let's have a look at the microscope and see what it consists of and how it works. Okay, so one of the most important tools for any electronics repair technician is the digital microscope. Now, microscopes, they come in many different shapes and sizes. So you can get the types where it looks like a binocular and you look through it and you work at the bottom of the microscope, or you can use what I use here, which is a digital microscope. And the way this works is basically you have a box like this, okay, and it's got a HDMI output on the top, right? It's got an image sensor at the bottom here. The better ones usually have Sony sensors. And what you've also got is a power port to plug in your power, and you've got 2 USB sockets. Okay, now what I can do with this one is I can have a USB flash drive and I can put it into this port here, right? And what that allows me to do, the software for the microscope is actually built in to the housing, right? And what it allows me to do is I can save images that I can see through the microscope onto the USB flash drive. And what I can also do is I can also plug in a wireless mouse, and I can use the software to do various functions. As I say, the software for the microscope, it displays on the output wherever your HDMI is connected. So let's say you have your HDMI connected into a HDMI monitor. So what you'll see is you'll see the image that the sensor is picking up at the bottom, and overlaid on top of that you'll have the software that comes with the digital microscope. And what it allows you to do is it allows you to draw straight lines, put measurements into your images, draw arcs, and it has various functions that you can use. I'll show you that a bit later on, but essentially that's all it is. And what it also comes with is it comes with the lens. Okay, the lens looks something like this. Now this here is a manual focusing lens, okay, and if you can get other microscopes, digital microscopes that have autofocus, but they are a lot more expensive. For example, this kit here, which I purchased a couple of years back, I think I paid £250 for the whole kit, and it comes with a base, a metal base that you can attach it to, and you can raise the microscope higher and lower to get you a wider angle of view or a narrower angle of view, whatever you're looking for. So what would normally happen is, actually let me talk about these Barlow lenses. I'll just move this out the side for a second, and that's all there is to this piece here, right? So now if you have a look here, the microscope lens, the kit will usually come with a set of, they're called Barlow lenses, B-A-R-L-O-W, Barlow lenses, and they come in various magnifications. So you can see here there's a 2x magnification lens, and here there is a 0.5 times magnification lens. And if you change out the lenses, what it allows you to do is it allows you to get closer to your workpiece, so you can get a larger picture basically. So the closer you get to your workpiece, and depending on what lens you're using, you can see a larger view of a smaller area, or you can see a wider view of a larger area. And that's essentially all the lens the lens kit that comes with it does. So what you'd normally do is, depending on what lens you need, is you would take your lens and you attach it onto the bottom here, like so, like I'm doing here. Let's do that, and that will give you a closer view or a wider view. Okay, and then what you can also do is when you get it onto the stand, right, you've got manual controls on the stand to raise this higher or to raise it lower, and that will also give you a wider or a narrower view. So let's take that off for now. I'll take that off, and I'll just put it to the side here. And it's the same thing with the other lens. And you can also get other magnifications in between these two magnifications and above them as well, depending on what your needs are. But that's something that once you start using it, you'll realize yourself, you know, what magnifications do you use the most, or what will be most useful to you. So what you do is, let's put these to aside for now. So what you'd normally do is you'd get your digital microscope base and you just screw this in to here, like so. Okay, and then what you do is you take this whole attachment and you fit it onto the microscope stand. So I'll quickly show you what the microscope stand looks like, and whenever I'm mentioning the microscope in the videos, you'll know now this is what I'm talking about and this is what I'm using. When you're choosing to buy a digital microscope, there's 2 points that I'd like to bring to your attention. One is the resolution and the other one is the frames per second. So in this day and age, there's no reason why you should go for anything below 1080p in the resolution, and in the frames per second you should be looking at a minimum of 60 FPS, right? And what that will do is that will give you a nice clear image, and the frames per second basically refers to the refresh rate of the image below the microscope displayed on the screen. So when you're moving stuff around below the microscope, the speed at which that image is going to refresh on the screen is related to the frames per second. So just bear those 2 points in mind, 1080p and 60 frames per second. Okay, so the rest of the bits that I'm going to show you now, these are also essential parts of your digital microscope setup. So what you normally get, if you order it as part of a kit, you'll probably get this with it, but if not, then you can order these parts separately as well. So the other important parts are the microscope base, okay, which is this bit here. And what we normally do is we get a heat mat and we place it on top of the microscope base. And then what we do is we put our workpiece on the heat mat, and if we're using the heat gun, that protects the metal underneath. If we're using the soldering iron, obviously if you get any bits of solder or anything all over the mat, then it's not an issue. Right, so what you also get is a stand for your microscope, and this stand here, it has adjustment knobs here that allows you to higher and lower your microscope. So what we would do is we would get our digital microscope and we would attach it into this hole here, right, like so, and there's a screw on the side that you can fix it with. And what you also have is you have an LED light here at the bottom. Now this LED light normally it's attached around here, but I find that that hinders my workspace. So what I've done is I've got two zip ties, one here and here, just like you can see on the side here, one here, and I've got a similar one on the other side, and I've attached it to the adjustment knobs, so it just gives me a bit more open area here when I'm working with the boards. So that's basically all it is really. You've got your base, you've got a stand, and then you've got adjustment knobs to go up and down. So whenever I'm talking about the, well, let me just show you what the LED looks like when you switch it on. So you'll have three cables coming in into your digital microscope, you'll have your HDMI cable, you'll have a power cable for the microscope, and you'll also have one cable here which is for the LED. So if we plug the LED in, you can see that comes on, and you've got a switch here that you can switch the LED on and off as well. Right, now to get your image out onto the screen, you just plug in your HDMI cable into the top. I'll bring the camera up here so you can see that. Right, so you can see here what I'm going to do is I'm going to plug the HDMI into the top of the microscope, and then I shall connect the power as well. And hopefully you should see the microscope coming onto the HDMI screen there. What I'll do is I'll make that a larger image so you can see that more clearly. Let me just quickly take a second to tell you about these chips. So I was able to order that replacement chip online, and I got them under the Philips brand name, and I paid £5, approximately £5.50 for 20 pieces, and I paid £1.65 for delivery. So that worked out quite cheap, and I'm quite happy with that. So what we're going to do now is we're going to take a closer look at these chips under the microscope, and I'll show you how the adjustment knob works and how the focusing ring works. Okay, so the way it works is really quite simple. As you can see, I have placed the chip onto the heat mat, and now what I'm going to do is I'm going to show you the image from the microscope that is displayed on your screen. Right, if you focus on the screen for a second, what I'm going to do is I'm going to switch on the LED, right, and then I'm going to use the focusing ring to focus the image of that chip. And if you can see on the screen over there is the display that is being picked up from the sensor inside the digital microscope. So that's all there is to it really. If you want to move more closer, you can bring the microscope down further and you can adjust it even more to get an even closer image, right? If you want a wider angle view of what you're looking at, you can take the microscope higher, right, and then you can adjust it from here and you get a wider view. And that's all there is to it really. That's all there is to the more or less to the digital microscope. And the reason why I prefer the digital microscope over the binocular type ones that you look through is because I like to see a large image of what I'm working with. As I say, it's just a matter of personal preference whether you like to use the binocular type ones that you look through and you see the image underneath, or whether you like to use a digital one like this where the picture is displayed on a screen separately. Now, one thing I want to make you aware of is that when you start working with a digital microscope like this where you've got the image coming out on a screen, at first you're going to find it a bit difficult to get the orientation inside your brain right, because you're looking up there and you're working down here, but the human brain is so amazing, and over time it can adapt to just about anything. So all you got to do is just keep practicing, and you'll get to a point where your hand coordination with what you can see on the screen will just become second nature, and you wouldn't even need to think about it. It's like when you're driving a car for the first time. You have to think about changing gears. This was before automatics came out. You have to think about where you're putting your foot on the brake or on the accelerator. Then you also have to hold the steering wheel. Well, it's a similar sort of thing. When you first start, you're always thinking about what you're doing, but eventually you get to a point where you're not even thinking about it. It becomes second nature, and you can drive while enjoying the views at the same time. So it's the same sort of principle with the digital microscope and a separate screen. You get to a point where you won't even notice it. Your brain won't even notice it, and you'll be working away, and you'll be thinking, how much I struggled when I started and how easy it is for me now. Anyway, that's most of the key points about the digital microscope. So whenever I'm referring to the digital microscope now, or whenever I'm talking about the digital microscope, you know now exactly what I'm talking about. Right, let's move on to the next part of the video. We are going to change out our faulty component on our PCB very soon, But before we do that, I would like to introduce you to the second tool that we're going to be using today, which is the soldering iron. Now, the soldering iron is a very simple tool. It consists of three key components. Those components are the base, your handpiece. I've got two handpieces on this one, and I'll explain to you what they're for in a moment. And then you have various bits that you can use that you attach to your handpieces, right? Now, most of the work with the soldering iron are going to be between 200 and 350 degrees, and this is what the base is used for. You set that temperature on your base, okay, and that determines how much heat will be transferred to your handpieces. Now, depending on the size of the workpiece that you're working with, you will select a bit to be attached to your handpieces accordingly. If you're working on one leg of an IC, then you will need a smaller bit that you will attach to your handpiece. And if you were working on, let's say, the fixing points for a HDMI socket, then you would use a larger bit attached to a larger handpiece. And the reason why we do that is because when we're working on small items, we don't need to transfer as much heat to the part that we're working on. But when we're working on a larger item, then we need to transfer more heat to that part, because that part is going to eat up the heat, and a small handpiece will not do the job in that situation. So let's get back under the demonstration table, and I want to talk to you a little bit more about these handpieces and the bits that attach to them. Okay, I just want to take a couple of minutes to talk about different size handpieces and their applications, because this is also very important. So as you can see here, I've got three different handpieces. This piece here is referred to as a T245 handpiece, right? Then smaller than that, we have this handpiece here. This is referred to as a T210 handpiece. And this piece here is the smallest one that I've got in my collection. This would be the equivalent of what we would refer to as a T115 handpiece. Now, the reason why we have different sizes of handpieces is, for example, let's say you're working with this component here. Now you can't see this, but when I bring it closer to the camera, you'll see what I'm talking about. If you were working on this component here, and if I can bring that in here, can you see how small the balls are on here? I'll show you this under the microscope as well, but if I could take this up here, you could just about see it's like a microcosm scale, basically, right? So when you're working on something this small, the lighter your handpiece is, the easier it is going to be for you to maneuver under the microscope, because sudden movements, little movements, is going to have a big effect, right? So the smaller the handpiece is, or the lighter the handpiece is, when you're working with small components, the easier it is going to be for you to do that work, right? Now, if you were working on something like, let's say, the IC that we're going to be working on, which is this one here, obviously, as you can see, this is a bit larger, right? So in this case, we could use a larger handpiece, and that will come with slightly larger bits. So the smaller the handpiece, the smaller the bits that come with it, and the larger the handpiece, the larger the bits that come with it. And the reason why we have different size bits is because, let's say for example, you're working on this here. This here is a HDMI socket, right? Now, as you can see, it's made of metal, and the fixing points are quite large. So if you were to try and heat up this part here with a T115 handpiece, you'll be trying to heat it up all day, and you probably wouldn't even be able to get to the temperature that you want to get it at. Whereas if you came in with a T210 handpiece, right, you'd be able to heat that up fairly quickly. And the reason why we need to be able to heat that part up fairly quickly is because we have to get the metal or the alloys to a certain temperature to get the solder to adhere to the component that you're working with and to the board. So that is why we have different size handpieces and different size bits for different applications. A few more things that I would like to mention while we're here is that you do not have to have the best of the best when you're starting out. What I usually say to people is, look, start with one handpiece, and the handpiece that I recommend is the T210, right? And then what you can do is slowly you can add more handpieces as you get more experience and as you work with different electronics devices. So the T210 for me, in my experience, is the most versatile because you can get medium-sized bits for it and you can get micro-sized bits for it. And you also need a larger iron. So the T245 would be ideal in that situation. These handpieces here are made by JBC, and this is a no-name Chinese brand here, which I have for the T115. Now, you can get these handpieces now, clones of these handpieces and clone stations from AliExpress. There's so many of them. I mean, you could make a video just about those stations. There's so many stations out there now. Now, what I would say to you is, if you're going to pick up one of the cheaper Chinese stations, one of the clones of the original JBC, then one thing I would recommend is that you buy the original bits, right? So even if you buy a clone handpiece and a clone station for about £100–150, make sure you buy or try to buy the original bits, because there is a day and night difference between the quality of the bits made by JBC and the bits that are manufactured by other manufacturers. That's the only key thing that I would say. So you can pick up a clone handpiece, you can pick up a clone base station, that's no problem. But if you want to save yourself a lot of headache, try and get the original JBC bits. They're a bit more expensive, but there is a night and day difference in the quality of the bits from my experience. Right, so what I'm going to do now is I'm going to take you under the microscope and I'm going to have a closer look at the most common bits that I use, and I want to share that information with you as well. Okay, so for the larger T245 iron, I primarily use two bits the most. One is a bevel bit and one is a flat bit. The model number for the bevel bit is 260052, and the model number for the flat bit that I use is 255885. So those are the two bits that I primarily use with the T245. For the T210 handpiece, the bits that I use the most are these bits here. From left to right is a 4mm chisel, a 2.5mm chisel, a 1.3mm chisel, a 1.3mm conical, and a 0.4mm chisel. Those are the bits I use for the T210 handpiece. And for the T115 handpiece, the smallest handpiece I have in my collection, I use I believe this is a 2.5mm blade bit, and this is also made by JBC. So whenever I talk about the soldering iron in the repair videos now, I'll refer to the different handpieces that I'm using and also the different bits. And now that you've understood and you've seen how it all works, it should make everything a lot more easier for you to comprehend. Right, while we're here, I just thought I'll quickly show you a close-up of the different size components, and that will give you a bit more perspective as to why we would need different size bits and different size handpieces. So if you have a look here, the first micro component here, which is an IC, the balls of this IC are underneath, right? So these balls are probably 0.2 to 0.4mm wide, and now you can understand why you would need a 0.2mm bit. This here is the IC that we're going to replace today, and these are probably about 1mm thick each leg. So if you try to use a 0.4mm bit on this, it would take too long to heat up, right? But if you use the right size bit, you'd be able to heat that up correctly, and when you apply the solder, it should adhere straight to the part and to the board. And if you have a look here, we've got one of the legs of our HDMI socket, so that you can see is significantly thicker than the other components here, and also it's connected to a larger piece of metal. So for that, if you were trying to use the T115 handpiece or the T210 handpiece, you probably wouldn't be able to heat it up as fast and as well as you would with the T245 handpiece and the larger bits that come with it. Right, we've got our PCB under our microscope. Okay, we have focused the image. Remember how I showed you how to focus the image earlier on? Okay, and this here is the IC that we want to remove, the faulty IC. Now, what you gotta bear in mind here is that the solder on these legs here of this IC, most factory IC, it melts between about 270 to 280 degrees, right? Now, we have to come in with a heat gun and we have to heat up the solder on these legs here to about that temperature. But if we do that, what we risk doing is heating up the other components as well. So as we're heating this up to temperature, these will melt, the solder on the nearby components will melt as well, and because we're going to be using wind pressure through the heat gun, there's a chance that some of these components might blow off the board and we might lose them, right? So we don't want to do that. So what we want to do is we want to bring the melting point of the solder points of this IC here, we want to bring it down much lower. We want to bring it down to about 180 degrees. That way, when we heat up this component, it will melt at the solder points here on this IC will melt at about 200 degrees, and we can easily remove this component without affecting any of the other components on the board. Okay, so I quickly want to take a couple of minutes to explain to you about some of the different types of solder that we use in electronics repair. Now, I'm not going to go too much into it, but every time I use a different type of solder in subsequent videos that will come in the future, I will tell you what we use them for. But for now, I just want to briefly explain to you what it's all about. So, if you have a look here, we have a low melt solder here in a tube form, okay, and this one here is a very low melt solder. It melts at, if I'm right, about where is it gone, at 138 degrees. Okay, we use this to lower the melting point of the solder on the board. Okay, then we've got a different one here which we use in different circumstances. This one here melts at 183 degrees, and this one is also in paste form, right? You can use a toothpick if you want to, let's get this to, yeah, you can use a toothpick to get some of that out and apply it to different areas of your board. Or we use this when we're doing stencil work. Now, I'm not going to go into that now because that requires a video all by itself. But when we do that in the future sometime, I'll explain to you what stencil work is and in what situations we use it, right? And then what we've got here is we've got various other spools of solder here in different thicknesses. So we've got a couple of 0.2 millimeter spools here, and they also come in different combinations of tin and lead. So the one that we most commonly use is a 6337. Okay, so that's 63 parts tin and 37 parts of lead, or 63% tin and 37% lead, right? We've got another one here which is from China. This is a 6040, right? 60 parts tin and 40 parts lead, and there are situations where you'll use this to lower the melting point of solder as well. And there are some situations where this solder is ideal instead of this solder here. But again, when we do future videos and I get into a bit more detail, I'll show you in what situations we can use them. And these are basically just larger spools of 6337, and this one here is a thicker spool of 6337. So when you're working with smaller handpieces and smaller bits, you do require a thinner piece of solder, because if you can imagine, if you're trying to work with a very small handpiece and a very small bit on that handpiece, let's say 0.2 millimeters or 0.4 millimeters, then this solder here, which is 1.3 millimeters in thickness, this is no good to you because it's too big, right? Your soldering iron is going to take, or your soldering bit is going to take too long to melt this, and it's just a bit flimsy. So in that situation, you would want to use a 0.2 millimeter diameter solder, okay, because it's much more suitable for the job at hand. So Again, I don't want to overcomplicate this. This series is for beginners, so I just wanted to give you a brief explanation of some of the different solders that we use. Now, for the job that we're going to be doing now, to lower the melting point of the IC, today we are going to be using this low melt solder here. As I say, it melts at 138 degrees. So once we mix up the alloys of the solder that's on the board with this solder here, that should bring our melting point down of the solder on the board to about 180 to 200 degrees, which is perfect. And that will easily allow us to pop off the IC in no time. So now what we're going to do is we are going to attempt to remove this faulty component. But before we do that, we want to mark where pin 1 is for that IC that we're going to remove. So what I'm doing now is I'm going to take a Q-tip, put some alcohol on it, and I'm just going to go over the component here, and you can clearly see here that pin 1 is on this corner here, denoted by this dot here. So what we're going to do is we're going to put a mark on the board with a marker, and that will help us remember when we replace the chip that pin 1 is in this corner here. So let's do that now. I've got a marker here, and I'm just going to put a dot in this corner here. Right, so if I put a dot about here, that should be fine. Okay, so now what we're going to do is we're going to put some flux around the pins of the IC that we're going to remove. So let's do that now. It's quite warm today, so the flux is coming out quite easy and it's flowing quite easily. But when it's cold, it's a slightly different situation. But that's fine for now. Alright, and what I'll do is just to give it a bit more protection, I'll put some around here. Okay, so now what we want to do is we want to put a little bit of low melt solder on the top of the IC, just like so. Now what we're going to do is we're going to set the temperature of our soldering iron on our base station to 350 degrees, and we're going to be using the T210 handpiece, and we're going to be using the 4mm bit. Okay, and what I'm going to do is I'm going to take the low melt solder and I'm just going to melt it and apply it on top of the pins. Okay, now what we're going to do is we're going to get our heat gun. We're going to set the heat to about 350 degrees, and we're going to set the wind speed to about 40, and we're going to use it to heat this up and lift this component off the board. But before we do that, let me quickly explain to you what the heat gun is and how it works. The third tool that I would like to introduce you to today is the heat gun. And the heat gun is a very simple tool. It consists of a base station and a handpiece, and it has different heads that you can attach to it. Now, the way it works is it's very simple. You switch it on, okay, and you have two settings on either side. You have a temperature setting, which you can set from 0 to all the way up to 500 degrees. Okay, we normally work about 375. And you also have a wind speed or a air setting that you can set from 0 to 100%. Okay, now these settings here, they will vary depending on what you're working on, and there's no one setting for everything. There's different settings, and depending on what you're working on, the thickness of the components, the thickness of the board, this is something that will come with experience. Okay, you'll start to figure out just by looking at a scenario in front of you, you'll be able to tell, okay, this is the wind speed that I need, and this is the temperature that I need. So don't worry too much about the settings. All you need to know is that it's a base station, and you set the temperature and you set the airspeed, and the temperature obviously relates to heat, and the airspeed is the intensity of that heat that you want to attack whatever you're working on with. And that's basically, in a nutshell, all there is to the base station. Now what you can also do is you can set, on this particular model here, you can set 3 different temperatures and you can save them into memory. Okay, and now what I'm going to do is I want to go to the handpiece, and I want to talk to you a little bit about the handpiece. So let's do that now. So the other part of your heat gun is your handpiece, and what it consists of is a rubber pipe that goes all the way back into the base station of your heat gun. Okay, and what it does is there's a fan inside the base station, and that provides the wind pressure which comes all the way through here. And in here at the tip there's a coil that heats up, so the wind pressure comes through that coil and it comes out the end here, and it attacks whatever you're working on. Okay, so the question comes up, why do we need a heat gun? Why can't we just use a soldering iron? Well, what it is with the soldering iron, let's say for example you've got a component here, and that component has 8 pins on each side. With a soldering iron you're going to come in and maybe you can heat up 3 or 4 pins, right? But you've still got another 4 pins on this side and another 8 pins on the other side, so you want to remove that component. By using a soldering iron you cannot remove that component, but if you come in with a heat gun, what you can do is you can heat up that entire component, and all the pins on that component, the solder that's on them, will melt at the same time. And what you can do is you can come in with your tweezers and you can just lift that straight off the board. Now, with the more modern heat guns, you have like a metal base that you get with it, and as soon as you sit the heat gun down, it will automatically switch off, right? And when you want to switch it on, you've got like a switch here on the handpiece. You can press that and that will switch it on. Okay, now you've got various bits that you can attach on the end. You've got angled bits here, and you've got straight bits here. You've got larger sizes and you've got smaller sizes. Sometimes you may not want to come straight down from the top with a bit like this, because maybe you've got a microscope in the way, right? In that situation you might want to use an angled bit like this, because it allows you to hold the heat gun at a certain angle, right? And then you've got different types. For example, this one here on the bottom, this will give you a swirling kind of wind pressure, right, on whatever you're working on. And this one here I think is a straight through. I mostly use the straight through type, and my most common bits that I use on the heat gun is this bit here and this bit here. So in a nutshell, the way I would describe it to you, a heat gun is just like a hairdryer, but it's a much more precise version. Just like on your hairdryer, you've got it on one button, haven't you? You've got low heat, medium and high heat. Well, with your heat gun you can set the precise temperature and you can set a precise wind speed, right? And people sometimes ask, oh, what's the ideal temperature and what's the ideal wind speed? That's something that is going to depend on each individual case, and that's something that will come with experience, and that's basically all there is to the heat gun. So let's get back to our repair. Right, so we're back at the board now, and as I was saying, I'm going to set the temperature on the heat gun to 350, and I shall set the wind speed to about 40. There we go. So let's do that now. And as you can see, that just lifted off the board very easily, and we never affected any of the other components around the board. So what I'm going to do now is I'm just going to quickly clean up that area with some isopropyl alcohol, and then I shall proceed to clean up those pads and prepare them for the new chip. Right, what I'm going to do now is I'm going to apply some fresh flux over those pads, and I'm going to retin those pads. So let's do that now. While I was reapplying solder to those pads, and at that point I had pressed stop on the record button because I was turning the board around, and what I forgot to do was press the record button again, so I've missed out all the bit of me reapplying solder to those pads, reattaching the new chip, and then going over the pads with fresh solder to make sure everything is attached correctly. So I do apologize for that, but that's basically what I did. I cleaned up the old pads, applied fresh solder to the pads, sat the new chip on top, used the heat gun to heat up the whole area here and get it to adhere slightly to the board, and then I went over each pin with a smaller bit. I used the 2mm bit, and I went over each pin and I applied solder onto each pin individually. As you can see, it's all done. You haven't missed out too much, and I'll be going over this kind of stuff again in future videos. So we've attached the new IC, and now all that remains for us to do is to switch it on and to see if everything worked. Okay, so after I fitted the chip, what I did was I checked all the pins in diode mode, and I can confirm that all the readings were matching with the working board. So now what we're going to do is, we've got everything on the bench. I've also got a microphone here, and we're going to switch it on and we're going to see if everything worked or not. So let's switch on our power supply first, and let's set the voltage to 15 volts. Right, and we'll set the amps to, set it to 2 amps. Okay, and let's put our power supply on. And now what we're going to do is we're going to switch on the receiver, and we can see that the receiver has switched on. And now what we're going to do is we're going to switch on the transmitter. Okay, and you can see that the bars are displaying here on the screen. Now what I do want to do is I also want to do a sound check as well, just to make sure that the sound is working fine. So I'm going to plug this in from here. Right, and let's pick up the microphone, and you can already see that it's starting to move. Test check, 1 1 2 3 4 5. Test check, 1 1 2 3 4 5. Okay, so we can confirm that's all working now. Let's get back to the demonstration table. The purpose of this 4-part series of videos was to get as many people interested as possible in electronics repair, and I hope that we have achieved even a little bit of that purpose with the work that we've been doing. What I was trying to convey to you was that learning theory is good and it's important, but you won't really get a grasp of everything until you start getting your hands dirty. And that's what I want you to do. I want you to go out there and I want you to start getting your hands dirty, meaning go out there, mess about with stuff, take it apart. You're going to make mistakes, but making mistakes is part of learning. So take stuff apart, see if you can repair it. If you can't, try something else and keep trying, and eventually you will get better and better. And that was the whole point, really, just to give you that initial push and to let you go out and grow yourself in your own electronics repair journey. There's still a lot more to learn, and there's still a lot more that I have to cover. So make sure you like and subscribe and watch out for future videos. Bye for now, and have a nice day.